Hey guys, like I said, today's lesson is going to start introducing us to something that is a little bit of a mind warp. Okay, so what I'd first like you to do before we do anything is I'd like you to go ahead and solve these. Solve each of these. In other words, right, what value of x makes this true, and so forth. And some of these will be easy, some of these will be hard. Okay, I don't want you to use a calculator. I want you to just do this in your head. So please pause and do these on your own, and then we'll come back and reveal the answers. Okay, so hopefully you're back. Now, I'm not going to do too much explanation with these. Some of these I think are very self-explanatory, but I might talk about a couple. So first one here is 5. The next one is 4. The next one, well, what's happening here, right? Well, I'm taking the square root, and what does x have to be? 1/2. So make sure you remember that one. Now, what's going on here? I know that this is 5 squared, but it's down here. So that just means that this has to be a -2. Okay, hopefully you remember that stuff. Okay, again, these will be the same sort of thing. Look at what's happening here. I'm reducing this down by what? So you have to think of how many powers of 3 got me to here, and that would be 4, so that's 1/4. Okay, the next one is -3. Now this one, I hope it's not tricky for you. Whoops, darn it. It's a 0, right? Anything to the power of 0 is 1. And the last one, I think you already saw that, is no solution. Okay, so an interesting thing about all these, I think you can see have exponents, but there is nothing, right, as a base that you can just go ahead and the exponent turn it into negative. Okay, so this is a no solution here. Okay. Okay. All right, so again, I want to kind of set this up, our new concept today, with talking about some stuff that we already know. Parent functions. So here's the ones that we'll work with a lot of the year. Basic polynomial functions. And that's functions in this sort of situation, right? Anything where the leading power is to the first, it's linear, we have quadratic, we have cubic, and anything with and this is any natural number, so 1, 2, 3, 4, 5 on, would be a polynomial function. So these are polynomial functions, and they have a lot of rules that we'll get into in later lessons. But some of the other functions we've done this year, right? We've played with the square root function, rational functions, absolute value functions, and exponential functions. And these exponential functions we, of course, have played with as far as finding like growth and decay and things like that. But one thing that one of these functions we haven't done is shown how to be able to isolate a variable. Because all these, when we start making equations out of them, we've got to get down to a point where we can isolate a variable. And we know how to do it with all polynomial functions, and we know how to do it with all of these functions, but we don't know how to do it with this exponential function. So we don't know yet how to isolate that. So when we would be solving equations, we were kind of forced to bust out our calculator and graph a solution. So those days are, for the most part, gone. Okay. So like I said, this is an exponential function. And the new family of function that relates to that is called a logarithm. Okay, a logarithm. And that's what this logarithmic function looks like. That is a logarithm. So this b down here is a base. Okay. Now on your calculator, if you were to look at your calculator, and I don't want to go too far into this now, you'll see a log button on your calculator, and this is presuming that this is a base 10. Okay. So this is called a common log. So, but typically we have to state that base. Okay. This is our input to the function. In logs, we often and probably mostly talk about that as an argument, the argument to the log. And of course, y, just like any other, is an output to the function. Okay. So just using what you like, again, a little bit of intuition here. Pause this and go ahead and tell me, what do you think log 2/8 is? And the same thing with log 5/25. Okay. Okay. So you might have just looked at these numbers and thought about what they might mean. I have a feeling you guys probably got this right as we look at this. Okay. And if you don't notice, basically it's like this. And I'm probably going to say this 10 million times. So it's 2, the base, raised to the power of 3, returns 8. And that's the way we like to say it. 2 raised to the power of 3 returns 8. So notice the base and the power are on opposite sides of the equation sign. So that's going to play an important role of all the stuff we do. Okay. Okay. What would this one be? Well, you're raising 10 to what power to get up here to 10,000 to the 4th? What do you need to raise 9 to get to 3? Well, this is smaller, right? What is it? It's the square root of that, so I have to raise it to that. The 1/2 power. And then finally this one. Okay, 2 raised to what is going to get me to here? Okay, well again, notice that this is in the denominator here, so it's going to end up being a negative. Okay. Again, this is just a beginning, so we'll jump into this more. So now what happened here? Oh, that's what happened. Okay. So now these are all in a logarithmic form, all these 6 expressions here. We're going to convert these into an exponential form. And just like I said before, it's just 2 to the power of 3 gives me 8. These are equivalent expressions. Over here, 5 to the power of 2 is 25, and so forth. Notice what happens. 3 raised to the power of 3 returns 27. So if I'm going to write this in its exponential form, well, what would I do? Well, base raised to the 4th returns 10,000. Okay. So that's an equivalent expression as I go into here. Now, of course, once you get here, you could, of course, convert that to square root if you wanted, but you can leave it as this as well. And then here. So these are the exponential form, and the others are logarithmic form, and they are equivalent, entirely equivalent. These mean the exact same thing. Okay. Okay, so let's come back and look at what we just talked about. B, right, our base raised to the power of y returns x. So these are related and equivalent, and we're going to use these to actually find some, to solve problems and other things. Basically, if you look at what you see right here, and this is essential, and this is why it's so hard sometimes, logarithm, because the logarithm is an exponent. Okay, you go, well, wait, what? Well, look at what's happening here, right? B raised to this, y. Well, what is y? Well, aren't we saying that y is just this? So can't I replace that here? And the fact is I can, okay? So a logarithm is just an exponent. And notice what happens there. And also this seems like vaguely familiar because I have a logarithmic function and I have a exponential function. And so basically it looks like I'm taking this and I'm plugging it into here. And when I plug it into there, I have the input of x, but then I have an output of the same thing. Huh. Seem to remember that we have names for those, right? Okay, so let's do a couple of really quick problems and convert. So I have something here in exponential form. Take a second, pause if you need to, and then write this in a logarithmic form. Okay. Hopefully you did try that. So the way you do it is you go, okay, so I'm going to convert it into a log form. I need the log. Okay. Log of what? What's my base? My base is 1/2. Okay. And it's raised to the power of -4. Remember where that goes. So leave a little space here, right? It's to the power of -4 and it returns 16. Okay. So notice how we did that. Let's try another one. Okay. Pause and do this one. Okay. Hopefully you recognize we're going to a logarithmic form now. Log base of what? 64. Okay, raised to the, and that's when as soon as I say raised to the, I put that equal sign in here. The power of 1/3 returns 4. Okay, and that's just, if we look at that, 64 raised to the power of 1/3 returns 4. Okay. Okay, so let's look at the inverse of this exponential function. Okay, so if I go ahead and say this is an exponential function and I give it an f of x, what is my inverse of that? Well, I think I've already hinted at it already. So let's just look at what that means. Think about how we find inverses for any other kind of function. We do this, right? Y equals this. Here's our function form. Our step one would just be, don't we just exchange those, right? Oops, like that. Okay, so let's do that. Okay, we get here. Now the next step is to isolate y. So we've got to isolate this. Now, up until today, we really didn't have a way to do this, but now we do, right? Now we just go, all right, I'm going to rewrite this in its log form. This is our exponential form. Rewrite that in its log form. Well, what do? Log b base, right, is raised to, so we put that to the power of y, and it returns x. And so we've done that. We've actually gotten a way to get this out of the exponent and down here. And so that's our base, our argument, and that's now our inverse function. So these are our inverse functions, exponential and logarithmic. And we're going to use these for several different things, but I just want to kind of make sure that you understand that it satisfies all those sort of conditions that we have to have for an inverse function. So take this function, this particular function with a base of 2, and here I'm writing its inverse. Okay. So what should happen here is if I plug 3 into here. Okay, well, what happens when I plug 3 into here? Well, I plug 3 into there and I get an output of 8. Okay, so I should be able to take this 8 now and plug it into its inverse, right? And what should I get out? I should go right from where I started, right? I should get the 3 from where I started. And that's exactly what happens. Okay, you can verify that with your calculator if you like. If you don't trust me, your calculator has all the brains. Okay. Also, it satisfies the conditions of the graphing conditions for inverses. So I'm going to go ahead and use my calculator and graph these two. Well, what do you know? Stop and think. What do you know about the graph of two inverse functions? How can you tell? Like if you looked at them, what would they look like? How would you be able to look at, oh, I can tell they're inverse? Well, they've got to be symmetrical, right? They've got to be symmetric about this line here, right? Y equals x. So I'm going to go ahead and plot all these three into my calculator. And here's what I get. Here is our log function. It's a growth function. Here's our exponential function. You're very familiar with these. Then here's my log function. This is a brand new function for us, a whole new family of function. And yes, it does have asymptotes and all sorts of fun stuff. So that's coming. All right. Anyway, so tonight, please do this this worksheet, and we'll go ahead and check it over tomorrow. And notice what it is. If you need to go back and look at this lesson at all, please do. But right here, you're just going to rewrite this, right, in an exponential form. Turning down here on these problems, you're just going to take these and write them in a log form. Now here, you're going to rewrite them again here in exponential form, but notice now it's not numbers. Now we do have, some parameters, or variables if you want to call them that, but they're actually parameters in this case. But we just can go ahead and do that for here and continue on. So please do those, check them, and submit them.